First thing I will say is let's try and make this a bit interactive. So if you have a question, ask away immediately. Don't wait till the end. So if at the end you ask questions, I have to slip back earlier in my slides, I know you weren't asking questions at the right time. So I'm going to talk about build systems. So it's quite a techie subject. So who recognizes something like this? Put your hand up. Ah, perfect, my ideal audience. So this is a little snippet of Make. So Make was invented in 1976 to build computer software. And think about 1976. If you look at this little demo I've created, it's using GCC. That didn't exist for another 12 years at this point. It's using XC. That didn't exist for another few decades. So 1976 really was the dawn of computing when we got Make. So this little Make file very simply says, kind of, if I want to build main.exe, that depends on main.o having already been built, and then I run this action, just do the linking step. And if I want to build main.o, this depends on main.c, and if I actually want to do the action to build main.o, I just run this little step. So it's not very deep, it's not very advanced, but it's a very powerful mechanism that Make came up with. And this was the build system that has kind of set the de facto standard for pretty much since 1976. So this talk's going to be all about build systems, so let's define what a build system is. A build system performs the necessary actions to do something respecting dependencies. So in the little example we saw just there, the necessary actions would be running GCC, and respecting dependencies would be making sure that we've built main.o before we try and use main.o. And one of the clever tricks Make performs is if you build something and then change only a subset of your inputs, it'll only rebuild a subset of your rules. So this is the kind of, it only does what's necessary. And for this talk, we're just going to focus on general purpose build systems. So there are lots of build systems like Cabal for Haskell, SBT for Java. Every language tends to have their own build system. And we're going to focus on, we're going to focus on just general purpose build systems. So here are a pile of general purpose build systems. Sorry if you can't see the ones at the bottom on the back. Who has heard of at least one of these build systems? Perfect. Who has heard of all of these build systems? Okay. Do I have all but one? Okay. Perfect, because one of these isn't a real build system. So Simon, which one do you think isn't the real build system? Hippo. Hippo is indeed not a build system. But all the others are build systems. I'm going to assume that was a lucky guess. So there are lots of build systems, and this is just a tiny fraction. Wikipedia has a page of hundreds of build systems. And I've kind of grouped them based on a bit of their history and how they came to be and who invented them and when. So you've got Make, really old, this kind of first one. You've got Excel, the classic Microsoft spreadsheet. Well, that's actually just a build system if you think about it in slightly crazy terms. So these are the old ones. Then you kind of get to Ninja and Shake, which is the kind of, about just over a decade old, the kind of modern but not super modern. And then as we kind of get over here, we've got these three, Buck, Bazel, and Pants, which are kind of build systems coming out of the big tech companies, respectively Facebook, Google, and Twitter. And then over down here, I put Nix, because Nix is a package management, a Linux distribution-ish, and it's also kind of a build system. So we can think of build systems on this kind of general spectrum and think about how we might group them.
What is Hippo?
Oh, Hippo is just what I made up to check that no one was just putting their hand up live.
System is just nothing.
It is nothing. No. It is my son's favorite animal at the moment, which is why it's there. So, can we see if we can start to see if there are in these build systems? Was that a question?
No,
oh.
I'm just.
Cool. Actually, yes. It turns out that build systems form into, basically there are two choices a build system can make about how it's implemented. How it decides to respect dependencies, and whether it decides an action is necessary or not. And these are the only two interesting choices a build system makes. And furthermore, there are only 3 different ways that you can respect dependencies that people have invented. And I've graded these out because I'll talk about these later, but just to show you, there are 3. And there are only 4 ways you can decide on the necessary actions. And once you have that, you can shove all build systems into a box. More importantly than that, based on picking a box, I can tell you a lot of the properties about the build system. What are its strengths? What are its weaknesses? Is it good for my task or not? Just on this box. And even more amazing than that, it turns out this box is the best box to have a build system in, and no one's put a build system there yet. So this is kind of the work I've been doing for the last few months with some colleagues at Microsoft and Newcastle. And it's just mind-blowing that there's such structure in these unrelated build systems. Was written the best possible build system. So in this talk, I'm going to talk you through, I'm going to try and convince you that all those hyperbole I just stated are true by giving you enough detail that you could have drawn the box. And disclaimer, I wrote Shake, which lives here, and I'm currently writing a build system that lives just here in this mythical perfect box. So the first thing a build system has to do, or one of the things a build system has to do, is it has to respect the dependencies of the actions it's running. So if you say this action uses main.o, it must have built main.o beforehand. And the way it respects the and there are 3 ways it can respect the dependencies, which is essentially choosing the order in which to execute tasks. So deciding, should I do this or this or this? When can I do this? Can I do this before this or not? And I've called those topological, restart, and suspend, and now I'll just go through briefly what each of those 3 are. But before I do, I need to introduce some scary words. So they're so scary, I put them in scare quotes. So who's heard of the phrase monadic or applicative before today? So that's more than I was expecting. That's where the intuition comes from, but I'm going to talk as though you've never heard these terms before. So the basic question is, when I'm writing my build system rules, when do I tell you about my dependencies? So I can tell you at the very start of the program, before I've done anything else, I can tell you all the dependencies of everything in my program, or I can tell you just before I need them. So right at the end of the day. So I think the kind of best way to explain this, as with many things, is to make an analogy with food. Imagine if you wake up at the beginning of the morning and you have to tell me, as soon as you wake up, what you're going to have for breakfast, lunch, and dinner. And then you get force-fed that at the appropriate times. That would be an applicative build system. Whereas a monadic build system would be, you wake up, what would you like for breakfast? Oh, I'll have cereal, shreddies. Perfect. So you have your shreddies, and then someone comes round about 11:30 and says, what would you like for lunch? And you can now go, shreddies were a bit heavy on my tummy, so I'll have a small soup. Or, oh, I'm famished because I did a lot of work. I'll have a hearty steak for lunch. So it's the ability to change your mind as you're going and only kind of commit to things just before you need them. So if we take our kind of main example before, well, when I said that main.o only depends on main.c, that's not really true if you're a C programmer, because you also depend on all the headers you've hash included in your main.c file. So what you really should say is, I depend on main.c, and I depend on all the headers that are imported into main.c with a hash include. So I can say I need main.c, and I can say I need the includes of main.c. Let's imagine there's a little shell function that gets them for us. So if we said that main.c is itself an output of the build system, so there is a rule to produce main.c, whatever it does, then, well, this main.c, who thinks this is an applicative dependency? Who thinks it's applicative? Who thinks it's monadic? Call out. Applicative, indeed. This is an applicative dependency because before I start, I could have known that I'm going to depend on main.c. It's always going to be the same. Doesn't matter. What about the includes of main.c? Who thinks this is applicative? Who thinks it's monadic? Monadic, yes. So this one is using values that I've built during the build system to make future decisions on what I need. So that's the key difference. So how do we write a build system? Well, if you read kind of any introductory blog post on writing a build system, the first thing they'll say is build a graph of all your dependencies and then traverse it with a topological sort. And if you have applicative dependencies only, so if you can get all your dependencies in advance, that works great. So a lot of build systems use topological ordering as their way of respecting dependencies. This includes, say, make, buck, pants, ninja. Very common strategy. You just build a graph, figure out an order through it. So one order would just be everything at the first level, second level, third level, and then run it in that order. And from now on, you don't need to think about dependencies or ordering. Of course, that's restricted to applicative, because if you can't describe all your dependencies in advance, you can't build a graph in advance. So what if you want to do monadic build systems? So you want the ability to declare additional dependencies as you're going through. Well, for that, you have two techniques, restart and suspend. So with restart and suspend, you basically start building a rule. Any old rule, doesn't matter. If that rule declares a dependency on a rule that has not yet been built, you have a problem. What do you do? Well, there are two choices. You can either basically say, okay, well, this running rule, throw it away, just run my dependencies, and then schedule it to restart again later. And that's the restart approach. Or you can take that running rule, freeze it in some way, run its dependencies, and then unfreeze it. And that's the suspend approach. So both of these require you to be able to suspend, to either freeze or to kill your rules. So just from an engineering perspective, let's imagine your rules are running on a Java thread. Well, killing a Java thread is not a good idea, and whereas pausing a Java thread is possible, but it's memory hungry. So just the implementation choices can actually make this a lot harder, which is why a lot of build systems avoid it. And you can kind of see the trade-off. So if you're going to throw away work you've done, that's expensive because you've got to redo the work later. And if you're going to pause a lot of running computations, that can be expensive because they might be consuming more memory than they would be otherwise. Does that make sense to everyone, those three ways? Cool. So obviously, actually running some action and then throwing away the work you've done and then later on rerunning that action sounds like a bad idea. It sounds like a potentially expensive way of going. So the two build systems that use this, which are interestingly Microsoft's spreadsheet from before the dawn of time and Google's latest fancy whizzy build system, which seemingly both have picked this strategy, use tricks to try and cut down on the amount of work they need to throw away. So in the Bazel case, it uses an approximation of the monadic dependencies. So it uses the applicative dependencies to try and order things so it doesn't have to throw so much away. And in fact, it doesn't actually let users write monadic dependencies. So only the built-in Bazel rules can do monadic dependencies, which further restricts how many monadic dependencies it sees in practice. Whereas Excel has a really neat trick. it essentially keeps a list of what ordering worked last time, and then next time round, it tries the same ordering. So if it gets to the point where it detects that it needs to throw work away and put it on the end of the queue, it remembers the queue order that worked. And if the structure of the build system, if the kind of graph that it implies hasn't changed, it will zoom through it without any restarting. So this actually means that in practice, your Excel sheet will keep calcing faster over time as it finds a better order of your dependencies, which is a really cute trick. Yep. I don't know. So the question was, does it store that order on disk? I'm not sure if it stores it on disk. It definitely stores it on memory. It wouldn't surprise me if it stored it on disk, but I don't know.
I mean, Excel used to use a memory dump as its storage format. So
Yeah.
maybe.
Yeah, Excel used to use a memory dump as its storage format, so who knows? I guess with the XML encoding, you could probably see this if it really does. So we've said there are 3 approaches for respecting dependencies. There's the topological approach, which is nice and easy, nice and simple, doesn't require any kind of runtime support, but only works for applicative build systems. There's restarting, which may duplicate work. And there's suspending, which may be hard to orchestrate. So I wrote the build system Shake. So Shake's reason d'etre is monadic dependency. I'll read all the things at the bottom, so you don't have to at the back if you can't see them. So Shake's reason d'etre is monadic dependencies. That's why it was created, and that's the most important thing it does. That's kind of its big differentiator. And what it does is it uses continuations to efficiently suspend computations. And in fact, the first version used green threads, which is a reasonable technique in Haskell where threads are super cheap. So that's the rows in the table I showed you, and that's all 3 rows. So all build systems do one of those 3 things. So let's move on to necessary actions. So the idea of a necessary action is, last time I ran this compilation, this time, has the state of the world changed in a way that means I need to run this action again? Is it necessary to repeat this work, or can I skip it because I know the result would be the same? And there are 4 ways. The first one, the one that Make uses and Excel uses, is the dirty bit. So this is the idea that basically, with each rule, you have a single Boolean, a single bit value that says dirty or clean. And roughly speaking, if any of my dependencies are dirty, I am dirty. And so Excel implements this strategy by literally recording whether each cell is dirty or not. Make, on the other hand, uses a very clever encoding of the dirty bit. So one of the really beautiful things about Make is it's a really sweet spot in the design space where they didn't add anything to the file system. They didn't have to invent anything. They used things that were already there. And the way Make encodes its dirty bit is using file modification times. And essentially, if the modification time of any of your inputs is greater than the modification of time of your output, you are dirty because your inputs changed since you were last built. What's really beautiful about this trick is at the end of my build, at the end of build running a rule, when I write the file to disk, that updates my modification time, making this rule clean, because now its modification time is greater than the inputs. But at the same time, it kind of transmits that information to all the things that depend on me by changing my modification time relative to theirs, so setting all the other dirty bits with just a single operation. So I find that really elegant. So the one kind of caveat with a dirty bit is that you need to know your dependencies. The dirty bit doesn't store your dependencies, so you need to know them elsewhere. So if you've got an applicative build system, this works just fine. But if you don't have an applicative build system, you have to find some way of approximating your dependencies. And the way Excel does this is essentially by over-approximating what are the dependencies of of a rule. So for example, if you have an if with a conditional, a true, and a false value, if any of them have changed, Excel will recompute that cell, even if it never actually goes into the true or the false case. And if that's the only thing that changed, it'll still recompute it. So it really only works with applicative, but Excel just about makes it work. The next approach is something we've called verifying traces. So this is a very simple idea. Basically, when you run a rule, keep a lookout and record what has changed. Record what you observed when you ran the rule. So what did I depend on last time? And what were the values of the things I depended on last time? So for example, in the first thing, we might say main.o depends on main.c, which had the hash of 12 or whatever it is. And next time through, all you do is say, this trace I had, this verifying trace, has anything in this verifying trace changed? If not, then I don't need to rebuild it. So this is a kind of simplistic, just capture the state of the world, check the state of the world, skip. So it turns out one of the most interesting properties about deciding whether an action is necessary to run is what happens if something runs but doesn't change value. And this is the property of early cutoff. So if something runs, doesn't change, do you continue building the things that depended on it? If you don't, you have early cutoff. So I have a little very simplistic build system here. So util.h is depended on by main.o and util.o, and main.xe depends on both of those. So if util.h changes, say we update the copyright year, or we change the license the boilerplate our lawyers require us to put on the first 100 lines of every file, that will cause, we need to rerun the compiler to see if it changes the code generated. But if you use a modern compiler like GCC, they've done a lot of work to make it deterministic, so it doesn't really depend on irrelevant details like information in comments. So likely as not, the object files won't change. So now, at this point, do you need to relink them to make a new exe or not? So if I'm using the dirty bit strategy, who thinks I need to relink main.exe? Okay, so most people. So in fact, using the dirty strategy, there's no requirement that I do it. If it changes, if it rebuilds and nothing changes, I could set it to clean without making any of its dependencies as dirty. However, Excel doesn't do this in practice, and make can't do this because of its clever encoding of the dirty bit. What about with verifying traces? Would this give us early cutoff? Yeah, the answer is yes. With verifying traces, it's almost hard to not get early cutoff, because the obvious implementation would just do what you expect, would give you early cutoff. That said, Ninja, the build system the biggest build system probably uses verifying traces, doesn't do it early cutoff by default. You have to mark it as a request per file with restat equals 1. So that's one of the things to say about this stuff. This is about the theory, and then there's a lot of engineering that goes from the theory to the engineering. So I titled this talk Distributed Build System, because that's really where I've been that's really what I'm interested in learning about. So a distributed build system or a cloud build system is the idea that if I'm building something, but someone else in my company or in the world has already built it with this exact same code, then I just copy it off a central server without doing a rebuild myself. So this can be vastly more efficient in big teams, and you can make a build that would take hours locally just be a couple of downloads. So how do we actually do that in practice? So basically, you record the verifying trace, but along with the verifying trace, you record the actual file that the trace produced. You shove all those traces on a server so you can share them with other people, and then you just consult them, and if there's a matching trace, you download the object. There is nothing complicated to a cloud build system, it turns out. This wasn't obvious at first. However, there is a lot of engineering work involved to send HTTP files all around the planet and sync and make sure someone isn't uploading viruses into your cache and whatnot. So it's not trivial, but conceptually, it's actually not hard. And then finally, we get on to the last form of deciding if a dependency is necessary. And this is quite an interesting idea. So deterministic constructive traces. So imagine I can promise you that our compiler is deterministic. So it doesn't use the system time, it doesn't use the location of the binary, it doesn't use any of these kind of incidental IP address or anything. But given the same source code, it will always produce the same output binary. In this case, I can do some crazy tricks. So given only the inputs, so given main.c, I can describe main.xc just by knowing the fact that, well, main.o must have these properties. It must have this shape because it's deterministic. There can only be one main.o for this main.c. Therefore, there can only be one main.xc. So if I'm implementing this as a constructive build system, instead of talking to the server for each intermediate step, I can compute it locally using only the information I've got at hand. So this cuts down on network overhead, and it can make it more efficient. The problem with this approach is it doesn't support cutoff necessarily, because if the inputs have changed, then the output must have changed, because there's no way of kind of crushing together similar inputs at any intermediate stages. The other thing is, if this property isn't true, and in practice it isn't true for almost any build systems, you can compile executables locally that segfault when run because it assumed non-determinism, which isn't true. So it's a brave person who follows this approach. And it turns out Facebook is that brave company. So these are the 4 necessary actions. So we've got the dirty bit, we've got verifying traces, constructive traces, and deterministic constructive traces. And basically, you've got cloud build systems and local build systems. Dirty is kind of applicative only. Deterministic is the brave deterministic assumption. So what does Shake do? Well, Shake uses a verifying trace. But actually, Shake uses a very special, clever encoding of a verifying trace using 2 version numbers. So for each file, Shake records the timestamp at which it last changed and the timestamp at which it last built. And now you can do comparisons to say you're only dirty if your dependencies have changed since you were last built. And then you get the nice property that Make has of kind of propagating the dirty bit forward and backwards. So now we come back to this slide on build systems a la carte. Hopefully it now makes a little bit more sense to you. So I made a lot of bold claims. So firstly, can anyone remember any of the claims I'd made? And secondly, does anyone want to challenge any of the claims I made? Perfect. So I will say that there is, once you've got this basic framework, there is a lot of engineering to get a build system. And just because, say, for example, Bazel supports restarting, it doesn't mean they've exposed that feature to the users. So even all the power you might expect can be lost by bad engineering. But what you can say is that build systems like Make are going to struggle to encode monadic dependencies because of 2 decisions they've taken, both of which require applicative dependencies. I'll also say that of all the build systems on Wikipedia, I think basically all of them are in these 2 buckets. There really isn't, people aren't that creative when it comes to build systems. They're basically here and here. And that of the build systems that aren't in those 2 buckets, I've almost enumerated all of them. There's redo that goes here, and there's a few others that fit around. But by and large, there aren't many in the other space. The other thing is that Shake Head uses both the Head development version that isn't yet released, uses both verifying traces and constructive traces. And was that a question? And what shake does essentially is, if it sees a constructive trace it likes, it moves it into its verifying trace, and so it has its local idea of what are the best traces. And then if it can't satisfy a request from its very efficiently structured verifying traces, it will go to the constructive traces. It's hopefully the best of both worlds. I will say it isn't connected to an HTTP server, which makes the whole cloud thing a little bit useless, but it's getting there. And so this kind of examination of build systems was recently submitted to a conference called ICFP, and I found out on Wednesday it was accepted with my co-authors Andrei Mokov and Simon Peyton-Jones. So that's kind of the first half of the talk over. So if you have been saving any questions, now is the time. And after that, I'm going to go more into engineering. So Simon?
So these are really nice dimensions to analyze them. There's another dimension which I saw Facebook optimizing for, not directly in Bach, but in the developer infrastructure, which is that as a developer, you want to provide the developer with as quick as possible feedback on changes. So if your build system records the progress towards the cost to get to a test result, what kind of choices are there to sort of schedule your build as well to give fast feedback?
So yeah, I mean, the question was kind of what can we do to augment it to get more fast feedback? Good question. And Facebook optimizes that for other things it does, but not really for Buck. It turns out it's a really hard scheduling problem before you throw in timings. So I'm not really aware of anyone who does anything dramatically clever with timings. They do things clever with tests and failure analysis and all that kind of stuff, which is comparatively easy because you don't have dependencies. You more just have points in space, and you know how long each one costs, and you know the failure rate. So you can guess what it's going to do. But yeah, I don't think anyone's applied it to build systems, but they should. It would be fun. Yeah.
But then you do the compilation with shape, as far as I know is possible.
Yes, that is possible.
And does it then use the verifying tracing mechanism of Ninja?
So Shake and Ninja both have verifying traces. So if you build a Ninja file from CMake and then run that with Shake, it'll just treat it like a normal Shake file. So it won't use Ninja's verifying traces or Ninja's format. It'll use the Shake verifying traces. They just happen to be, so Ninja traces do the topological, so they're restricted to being applicative. Shake's ones can be monadic, but because the monadic is a strict superset, it's fine. It doesn't make any difference. Okay, on with engineering. So this is where we see some Haskell. I'm not sure if that's a good thing or a bad thing for this audience. Since I'm now talking about Shake, I'll show you the Shake URL, which is shakebuild.com, if you want to try it out. So I thought I'd tell you a little bit about how I got to Shake, but the clock's not got a lot of time on it. So basically, I wrote Shake, and there are 3 papers here. So what does Shake look like? Well, make looks like this. So you say, to produce this file, I depend on these inputs, and I perform this action. Shake, if you kind of blur and ignore all the syntax, looks the same. To produce this output, I depend on this input, I run this command. It's kind of like a very verbose encoding of make at this level. But the way it's encoded is it's a fully fledged Haskell program. So it builds on all the Haskell type system, and everything has a proper Haskell type and a proper Haskell syntax, which is partly why it's more verbose. And from that extra verbosity in the common case, we get extra power to do abstraction and other nice things. So you pay a little bit for the simple case, and you hopefully gain a lot in the complex case. So you've got essentially actions, which are basically a series of bash commands, if you're thinking make. You've got rules, which are basically the combination of an action and where to apply the action. And you've got this little funky %greater than operator that takes a pattern, so where to apply it, a action, what to do, to produce a rule. And you just put together a pile of rules, and that's a full build system. So this is a slightly longer example and a slightly more powerful example, making use of those monadic dependencies. So let's imagine we've got a file, result.lst, which is a list of file names. So imagine you're effectively saying, I am producing a distribution for my software package. I want it to include these 3 files. And then you want the output to be a file, result.tar, that actually has the contents of these 3 files in it. Okay? Easy enough in a monadic build system. And this is a complete Shake program, a complete Haskell program that essentially just imports the Shake library to do its stuff. And you can see essentially this rule body here looks very much like on the previous slide. But yeah, it's just kind of bridging the divide from a single rule to a Haskell program, a complete Haskell program with a main that when run will do what you want. So one of the reasons I started Shake was generated files. So let's imagine we have some source data, so say an XML file containing all the keywords in our language or all the time zones in the US, something like that. And we have some generator program that when applied to this source file will spit out a C file that we want to compile and then link into something else. So maybe we're doing an efficient hashing or a pre-compute or something like that. What does mySource.o depend on? Answers? mySource.c, and because it's a C file, and all the header files it includes. Exactly. So what header files does it include? Well, I could hard code it. So I wrote the generator. It probably includes studio.h. Maybe it includes util.h. I could guess in advance and hard code it. Or I can try and hack an approximation of my gen. Maybe I know if I see the XML element city in it, then that means it includes city.h. So I can kind of half reverse engineer the header part of my gen and bake that into my build system. This isn't looking good. I can, instead of having one build system, I could have 2 build systems. So I could build my source.c and then do another build to build the object from it, which is now I can look at it. Of course, having seen, if you remembered as far as applicative and monadic, you'll see there's also a really obvious answer, which is just use monadic dependencies. And then you just say what you want. Make my source.c, look at it, see what headers it depends on. You depend on those headers. It's easy, it's fast, it's precise, and it's compositional. So it kind of builds up very nicely. So people have spent a long time writing build systems without the power of monadic dependencies, which is really weird to me, because as soon as you have any rule in your build system that requires a monadic dependency, if you don't have a build system that can support monadic dependencies, basically everything starts going pretty pretty fast. The workarounds aren't compositional. The generated files, they just don't really work. So my advice would be, if you're starting a new project and you have any suspicion that the build system is going to grow beyond 100 lines or something, make sure you've got monadic dependencies there, because if you find you need them later on and you don't have them there at the beginning, you're going to have problems, and you're going to need to either find workarounds or convert to a monadic build system. Just so happens I have a monadic build system you can buy if you're interested. But I genuinely believe that everyone should be using a monadic build system, even if it's not mine. So what is Shake? So Shake is a build system with monadic dependencies and suspending, not restarting, using Haskell, and it's all about putting together the ingredients. There's nothing super inventive in Shake. It's just about putting these ingredients together and coming up with a build system at the end. So, for example, from Haskell, I've stolen basically a syntax, so I don't have to write a parser. I've stolen types, so I don't have to write a type system, and my build system is still well typed. I've stolen abstraction libraries, so you can package shake rules up as a package on the Haskell builds in the Haskell package system and share it with other people and do all the things you're used to doing with other code, because now build systems aren't special anymore. And because it's modern and it's engineering and it's in a nice garbage collected language, I can do things like profiling, lint, some static analysis on it, because these stuff is easy if you've got the right tools, and really quite hard if you're talking about a 1976 C code base. And of course, you want it to be robust and efficient. So put it all together, you get Shake. So I first gave a talk on Shake in 2012 when I worked for Standard Chartered. And at that time, it had been in use for 3 years. Now it's been in use for about 9 years. And when Standard Chartered switched from make to Shake, they went from 10,000 lines of makefile, which didn't work, was very slow, and was often wrong, to 1,000 lines of shapefile, which was correct, I think, twice as fast to compile from scratch. And when I started at Standard Chartered, essentially, if anything went wrong, the standard advice was make clean and try again, which was a multi-hour effort. By the end, once we switched to Shake, it just worked, and you could trust it. And having trust in your tools means that there's a whole set of debugging exercises you can skip when something goes wrong. If you ever used a dodgy compiler, very quickly you start thinking that every bug you've written is the fault of the compiler. And it's just an extra avenue you don't have to go down. Nowadays, Shake is used much more widely than just Standard Chartered. Practice Research GmbH use Shake to compile their checkpad med application. But the one I really like the most, the best use of Shake, I find, is Keystone Tower Systems. So these people build wind turbines. But rather than build a wind turbine in a factory, transport it along the motorway, and then put it in a field, they transport a little robotic welder and a roll of sheet metal to the field where they build the wind turbine in situ. And they use Shake for the build system for something for this. I don't really know what. But that seems very cool. So, of course, it's a modern build system, so you get all the nice features like progress reporting. So it predicts how long your build will take and then colors in your Windows taskbar very slickly, if that's your kind of thing. So this is saying it's about 82% complete. It'll take about another 3 minutes for you to finish. And this is quite useful. It tells you, do I need to go have a coffee? Do I need to go have lunch? Or can I wait? Is this one Reddit post away? So I thought I'd talk a little bit more about the engineering, about why Shake is fast. So I guess the first question is, what does fast even mean? And in build systems, there are really two extremes. Either I've changed nothing, and this build should happen instantly, or I've changed a lot, and what I really want to do is build everything from scratch. And most of the time, people change a little bit, but by optimizing the extremes, which require different optimization techniques, you can get a very good build system overall. So, to be fast if nothing changes, the first thing to do is not run any user's code, because users suck at coding. I've spent all this time writing a really optimal build system, really fast, tuning all the parameters, and they will do horrible things in the middle of it because they're users and because that's not what they care about. So the first thing to do when, to make builds fast when nothing changes is to not run any user code. And the verifying traces approach makes that very easy. For essentially, I just check that all the key value pairs haven't changed. And that's it. No user code required. And then there are all the usual techniques like avoid lots of locking, do it in parallel but not too parallel, so you thrash things, lots of things like that. And also, it turns out in practice, actually, writing the verifying trace to disk, so the serialization, is one of the bottlenecks, which is unavoidable in some sense, but it's a nice state to be in. So the other extreme is if everything changes. So if everything changed, you hope the user's rules dominate. So they're calling out to GCC, these are going to be slow rules. So basically, all you have to do is get their rules running as fast as you possibly can, and with as much parallelism as you possibly can. So the things that make that work better are having fine-grained rules that do just one action, so you can run more of them in parallel. And having monadic dependencies makes it much easier to express this fine-grained dependencies, because you're not limited in where you can split dependencies up. You can start spawning before you've checked everything. So instead of doing the kind of topological approach of build a nice graph and think about everything in advance, as soon as you see something that you think needs to go, fire it off immediately. Make use of multiple cores. Every build system does this now. It's not a big deal. But one of the nice tricks I found was actually if you take all your dependencies in your build system and run them in a random order, so just, literally, you've got the list, pick randomly from it, instead of going from one end, that makes your build up to about 15% faster. And this is a curious effect. So essentially, if you write a build system, usually you'll do a lot of compilation, which is CPU heavy, and then a lot of linking, which is disk heavy. And if you pick any natural order through this, you'll end up doing basically all the compilation at the same time, then all the linking at the same time. And they fight for the same system resources. Whereas if you just randomize the order, you can suddenly get better throughput, which is surprising, but cool. It also does tricks like continuation, monad, cheap threads, etc. So I've got 4 minutes to go. So the idea behind Shake is essentially all rules start either loaded from disk, because I saw them last time, or missing. At some point, I decided I need them this run, and I make them running. And after they've finished running, they become either ready or error. So this is the heart of Shake, is just a kind of state transition system which tries to put things in running and get them out of running. If you're running, what happens? Well, the first thing you do is, have any of my dependencies from last time changed? If so, I need to rebuild. Has the result from last time changed? Has someone deleted the exe that I produced last time? Okay, if so, I'm dirty, rebuild. If I'm dirty, but I can see an answer in the constructive trace, copy it in. So this is the cloud aspect. And otherwise, just run the user-supplied action. So it's not very complicated. The kind of basics is reasonably straightforward. I'm hoping you're thinking, I could have written this in my head. So the final thing I'll leave you with is some real serious hardcore tech that is incredibly simple and incredibly mind-blowing. So who's heard of continuations? Okay. I've been writing, Shake is very heavily based on continuations, so I've been working with them for years, and they still blow my mind. So you can think of a type as being a conversation. So if you, the audience, give me an A, that is this type. So it's like you have an A in your hand, probably because I asked you for it, and you give it to me. That has type A. Now, what if we instead switch to the type, this type, which for those of you not familiar with Haskell notation basically says, you're giving me a function, which when given a function does this. So you can think of this as, you give me a function, I then respond and give you a function, and to the function I gave you, you give it an A. So you're still providing the A, but you're not providing the A now. You're providing the A to me later. So, and it kind of inverts the flow of the program. So instead of me taking the A and doing what I was going to do with it, I give you the entire program I was going to run on that A, and I give it to you, and it's your responsibility to run that later. And so yeah, it's the difference between A now and A later. And if anyone's looked at covariant, contravariant, it turns out this is a really deep fundamental reason that essentially every time you hop over an arrow, you flip from covariant to contravariant and vice versa. So if you hop over 2 arrows, you basically end up where you started-ish. But this turns out to be a really efficient way to pause a running computation, because essentially every single time you have a value, you have the whole program that runs, and you're basically continually pausing the entire computation. So this is a really neat trick for doing fast and efficient suspense. So I'll skip the other things and go straight to the conclusion. So build systems basically make 3 choices: respecting dependencies, the necessary actions, and an awful lot of engineering. And I think Shake occupies a relatively interesting spot on the design space. Thank you very much.
So if all went well, we have no further questions because you asked them already. But just in case, we have 10 minutes left. So
Certainly. I mean, is that 10 minutes left? I was just following your clock.
yeah, I mean, 10 minutes were meant for the question part. But if the question is, can you please show us the slides? I guess we can also do that, right?
Cool. Okay, so I've shown you efficient suspend. The only thing left is efficient resume. Now, efficient resume is a lot easier side of the equation. So basically, this kind of state machine I showed you is basically an algebraic data type that says, well, a status is one of running or ready or wait or blah or blah or blah. And basically, inside running, I accumulate a list of the actions that I need to continue with when the running state transitions to being either ready or error. So essentially, I queue up my continuations just here, and when this thing leaves running, it's responsible for restarting all the things that were waiting for its answer. And one of the rules I have in Shake is essentially that because essentially you've kind of inverted the flow of control, I've asked you to do my work when you're finished doing your work. It would really be unfair if I asked you to calculate the millionth digit of pi when you're meant to be doing your work, and I've just kind of asked you to do something for me on the side. So when a computation resumes, what it does is it shoves itself into a thread pool. So Shake has a thread pool. Basically, the idea is you shove in actions, and it will run them for you at its convenience. So one of the things Haskell has is a very efficient green thread system. So whereas in other languages you would often use a thread pool to avoid the overhead of thread creation and thread teardown, in Haskell that's not necessary. It really is microseconds, nanoseconds, some irrelevant number of time unit. But what you do need to do with the build system where you're calling out things like GCC is make sure you're not running too many of these GCC-style computations in parallel. So the thread pool is all about limiting and making sure I'm not doing a kind of round-robin switch between the threads, but when I only start a new action when the previous action is finished. So, and then there's also the aspect of cleanup and making sure all the threads finish at a nice time and that I can finish them all together, etc. So, I mentioned kind of earlier that the journaling was quite a problem, or the journaling, the binary serialization was one of the most performance critical aspects of the system. So the way Shake does this is it essentially has a store of all the verifying traces, and it has append-only records at the end. So when it kind of calculates a new verifying trace, it just appends it at the end. So it doesn't have to kind of manipulate the structure. And each record is prefixed with its size so that if kind of the power goes out while I'm writing a record, I don't corrupt the whole database. I can see, this is where the database is corrupted, so throw everything away after that. And then I just do the trick that if I read the database and more than half of it is superseded values, I rewrite the database smaller with just the interesting values left in it. And then there's a flush every 5 seconds. So there are lots of engineering concerns here, things like on SSDs, you want to be really careful not to flush all the time on every action because you'll burn out the SSD too quickly. And yet, if you leave it too long between flushing the data to disk, then you can get to the problem of you lose too much work if things blow up in the middle. One interesting bug with the journaling system, so when I first wrote Shake, long time ago, it kept corrupting the journal every so often. And it turned out that if the hash of the file name contained the byte 13, then the journal corrupted itself from that point onwards. Any guesses as to what this was? New line indeed. I'd opened the file in text mode, not binary mode, and on Windows it was corrupting all my new lines. So, and now I'm back to the conclusions. Any further questions?
Okay, I think this is going to be a hard one to formulate, but you said that you're basically using continuations, so you hand over to the task that's going to be running all the dependencies and give it the responsibility to run those dependencies once it's finished. But you're also using parallelism, and so you could be running two tasks at the same time, which both have the same dependencies. And so how do you deal with this? There could be a conflict on who will continue running that one dependency that both depend on. How do you solve that problem?
So essentially, only one person can be running for any given rule. So if you're loaded or missing, then you transition atomically to running. But if you want to depend on a key that is already running, you don't start it again, you just wait for this guy to finish. So there's a lock, and it's basically the first one in is responsible for running it, and everyone else gets to wait.
Okay.
Does that answer the question?
I'm not quite sure if I get it completely, I'm sorry. So if I have a dependency that somebody else who's already running also has, then I don't get to be running.
No, you don't. You essentially wait on this person running. You are probably running a different task, so you are probably running on a different rule, and now this rule effectively blocks on this rule. So you kind of end up with the wait.
Oh, okay. I think I kind of get it, thanks.
Yeah. So this requires a bunch of locking in the middle. It's all a bit gnarly.
So anything in particular that you have learned about thread scheduling? Because it sounds like you have a lot of interesting scheduling problems there.
No, I wouldn't say so. I mean, I guess the thing that surprised me was that random thread scheduling is actually a valuable thing to do. Generally, people try and get randomness out of their programs, whereas it actually turns out there are quite a few instances in computer science. So like Quicksort has an n log n worst case if you use random pivot selection, but an n squared worst case if you don't. If you pick any systematic system, you can make it go n squared. But if you just use randomness, it's n log n. So maybe we should be looking for more, maybe it's just a kind of parlor game, but I kind of like this beautiful randomness saves the day trick.
Anyone else? Otherwise, thank you very much for the talk. Yeah.